All right, I think we can probably start. I can start by introducing the speaker. All right, so have you gotten your food for later?
Oh, yeah, yeah.
They are taking care. All right. It's my pleasure to introduce today's speaker. I'm Renato Mancuso. I'm an associate professor here in the computer science department. And today the speaker is Francesco Ciraolo, who is a PhD student in my cyber physical systems lab, so here at BU. And Francesco started at BU his PhD path in 2022 and has been working on what now is his brainchild, this idea of being able to virtualize resources. You see what we mean by that more specifically, without relying on software, right? And to understand how this is done, you have to a little bit enter a very fine-grained domain of how things are done in hardware. So today is going to be very, very technical. And I encourage all of you to slow Francesco down if you think that things are going too fast. We also have a demo, a proof of concept demo of how things start to work after a couple of years of working on this. All right. So without further ado, please welcome Francesco, who is talk on softwareless virtualization.
Thank you. Okay. Hello, everybody. I'm Francesco, and I'm gonna present my main project in softwareless virtualization. The idea is allowing a very thin layer of virtualization existing only in the FPGA, so in the programmable logic of a board, and using it to control the main CPU cluster software, running software, either operating system or other hypervisors, and virtualize them. So the main idea. Okay. The approach wants to be only hardware-based, and so it needs a piece of hardware. In this case, will be programmable logic, but also ASIC will be fine. It will allow a translation that is not only page-based, like it is right now virtualization, but it will be allowing also rules or semantic or any kind of more sophisticated way of translating and then virtualizing we can imagine. The activation or changing of the properties of this virtualization layer is supposed to be as seamless as possible and transparent to the software layer. We want to enable also a partial virtualization. The current systems, if you enable virtualizing layer, so stage 2 translation, we'll see later, it will be virtualized the entire system. There is no way to specify a page or a set of pages. What we can do, and we can prove it later in the demo, is virtualize just some piece of the system. The reasons, of course, can vary, but this is something we can do. And we want, as I told before, to be either alternative to software layer hypervisors or be additional. So in theory, not tested yet, it's possible to virtualize multiple hypervisors in the same machine and allowing them another layer yet of virtualization. And we want also to provide some kind of simplified configuration. So namely, we want to avoid the software layer to be specialized on the hardware running multiplexing or any kind of virtualization layers, and simplifying therefore the configuration of the virtual machines. But we'll go to this later. So, as said before, we are working in an hardware-based approach. Therefore, we need some hardware for testing, and perhaps for better exploiting of this technique. We will use the CPU plus FPGA boards, that are boards in which in the same system on chips, there is a CPU cluster, both with RPUs and APUs, and a slice of FPGA, so programmable logic, next to it. There are multiple current off-the-shelf solutions for this. The most common are embedded. So, for example, in our case, we will use an ARM-based system, but there are in program for the close future, the distribution of larger scale FPGA plus CPU machines, and with CXL interface that is going to be, I think, soon, we will have multiple systems allowing this. the only requirements we have for our theoretical softwareless virtualization is a memory map interface between the FPGA size and the CPU cluster size, and a cache coherence channel. Exactly as the multiple local caches of each CPU needs to be coherent with the last level cache and so on, also in a system in which there are multiple masters, for example, FPGA CPUs, FPGA accelerators, GPUs, next to the CPUs that can have local caches, and they want to be, of course, coherent for the distributed memory system, there has to be a channel only dedicated for the coherence of this cache line. So, this is a general overview of what is this approach of cache snooping. I will refer with the terms that are specific of the ARM64 system, but could be generalized to most of the system. So, when there is an access that is cacheable and therefore has to be coherent from the CPU package, from the CPU cluster to the DRAM, it will pass through a cache coherent interconnect that is a fabric, will take care not only of, in case, forwarding this transaction back to main memory, but also interrogating the other masters in the system. In our case, will be just our FPGA system, about the current usage or presence of this data in their internal cache. If there is a miss, therefore the other cache, the other coherent masters, in this case the FPGA, don't have cached this piece of data, defined by a physical address, so the address will be directly present in DRAM, then there will be a cache miss, and the CCI will forward this thread back to the main memory and provide the data that are currently in the main. It will be just a step, one step more, but in general will be also be parallelized. So that's the general context. Of course, if there is an IT in the FPGA or in the GPU, therefore will be this master to provide the last version of this cache line, modified or just easier to access in respect to main DRAM. Okay. There is a technique that's been developed by Shaheen in our lab. It's called backstabbing. So in this context, when we want to operate to alter the content of a cache line, we can reply always that we know the content of this physical address cache line. We don't have to be immediately, we don't need to immediately follow with the data, so we have the time to go back to DRAM ourselves, retrieve the current data in memory, manipulate the data, and provide it back to the CCI. So basically, the concept of backstabbing is hijacking the technology of the cache coherence in a non-provisioned way, and therefore be able to manipulate the data that will be passed to the main CPU. This will not be reflected on the main memory, so is an on-the-fly surgical transformation, and can be done at runtime. So there is no kind of configuration required from the software.
Does it make sense at this point? Maybe as a bit
the everything. Okay. So we talked about virtualization. We talked about cache coherence. We need to talk a little bit about the virtual address space or the virtual memory domain. A virtual address needs to be translated to a physical address, and in our case, so in a ARM64 bit processor with 39 bits of virtual address, will be composed somehow like this. There are some indexes that will be used for accessing, for referring to the indexes of each of the translation tables and the offset of the final page. We need, in order to have a virtual to physical translation, the page global directory, that is the address of the base of the first page in order of the translation when it will occur. And we need a memory management unit, that is an hardware unit that is instructed just to do this translation, having PGD and virtual address. How it works? We have this table, the PGD table, and we will use the first index, the 9 bits of the first index, to point of one of the index of the entries of this page table. This entry will be the base of the next table. And the second index will tell us where is the second PT is, and so on, up to reach our data page and use the offset to address 1 byte on this page. This is the normal virtual address translation. Of course, as I said before, if you want to add a layer of virtualization, we need a second stage of translation, because what is right now the physical address that is obtained at the end of the first stage of translation will now be considered an intermediate physical address, so a second layer of virtual addressing, and then needs to be translated again to an actual physical address in mainnet. We need a second table that will start the second stage of translation. In ARM, it's called virtualization translation table base. And, sorry, we can see this is the previous translation we had before. Now, if we add the virtualization between the previous last step, okay, between the previous last step and the actual data, there is a new virtualization stage. So this is the intermediate physical address that will be used again with the same context of index to translate the IPA to a physical address. Was I clear enough on this side? So this means not only that we are going to need an additional layer of translation for the last step in this graph, but for each of the indexes retrieval, because those are in theory physical address, but in the virtualized system will be IPAs, and therefore this process will explode once there is a second layer of translation. Okay, now why I started to discuss about these somehow disconnected points in systems, because we can connect some dots. Now, what is done by the MMU, so the readings for the next steps of the translation table, is actually a cacheable read, because in the distributed virtual memory system, so in which each master in the system needs to see the same virtual memory domain, also these snoops has to be cacheable. So they are snooped over the coherence channel. In general, we will see each of these MMU accesses from the FPGA side. And we have backstabbing. So whatever we see on the cache coherence channel, we can alter, we can manipulate, or at least we can take track of it. So it seems possible to manipulate the results of the translation, and therefore not only change the actual physical address of the data who is pointed by the translation, but also the attributes. It means we can change the cacheability attributes. It means we can change the access priority level. We can change multiple attributes that are defined and accessed by the translation level. Because not only the MMU will give to the main CPU the resulting physical address, but will also give a set of permission, attributes, and so on. And all of this can be modified at runtime.
It makes sense.
Okay, so what we want to propose is called right now software nano-virtualization, softwareless nano-virtualization. Well, we don't need hardware anymore. Softwareless nano-virtualization, my bad. And we consider it to be transparent to the software, as said before. So we don't need to instruct Linux in this case, or an hypervisor of the existence of this layer. And it wants to keep the minimum information requirements for being activated. In this case, what we need, of course, is the PGD of the process we want to manipulate, is the target virtual address. So which of the multiple virtual address or the multiple pages that will be referenced by this process we want to alter, we want to manipulate, we want to, in any case, to virtualize or take track of. And we need either a new physical address to point to or a new set of attributes, or a combination of the two, in order to actually operate on this PTE.
I think one thing it's interesting to highlight here is because it's based on PGD, you can actually do virtualization on a address space basis, which means you can virtualize an application under Linux and not virtualize another application under the same Linux, or virtualize resources of the kernel, but not of the application running on that kernel, and kind of anything in between.
Yes. Thank you. So, yes, please.
Specific virtualization. I see.
Yes. Of course, I mean, nobody stops us from using as virtualization space, they all Linux, okay? But we can also have something that is more surgical. That's the idea. That's
You could even go down to page level.
yes, yes, our granularity is page level. Okay, so of course, we don't know the full answer for this point, but from some preliminary test and from some assumption that I will now discuss, in theory, we will have a minimal overhead. Why this? First thing first, because we don't have to be actively operating all the time. We will just be passively responding to the snoops that will be received through the coherence channel. So basically, we will be activated once every time there will be a translation. But also translations are not so frequent because they will be cached, both in part or in total by the TLB, so the translation look-aside buffer. And therefore, we can also exploit the current system to limit the number of page translation to also the virtual translation, virtual to physical translation, to also limit our need to work through the operation of a process. Considering, of course, we are not using anyhow CPU time because the cluster does not need to run any kind of software to interact with SNV. Okay, now, yes.
Being on the coherence domain means you need to respond with snoops.
Yes.
Doesn't that slow down the coherence process itself?
In theory, yes. In practice, not so much for two reasons. There is a speculative prefetch. So every transaction that is snooped to the other masters in the system will also in parallel be retrieved by main memory. So every time we take the time to reply no, in any case, in the meanwhile, there will be a read to the main memory. Second point. And also because from our preliminary tests, these cache snoops are not being frequent enough to actually slow down the runtime of an application. But I will go back with this after we have more extensive results. Yes?
I just wanted to add, we're not the only masters in the coherence protocol, right?
Yes, but if we are, this could be a slowdown.
Yeah. You know how they say that if you're running from a bear, you need to be the fastest one, or you need to be faster than the slow one? Just to be faster than me.
So in theory, we should be good. Okay, so if everything has been clear, we can try to see the steps of this machinery and see if we also agree on the practical work. As I told you before, we are not actively doing anything during the runtime. We're just passively waiting on the cache coherence domain and see what happens. What we are searching for is an address that looks like this. It has the PGD base, a PGD PFN on the higher part of the address, an index, and some zeros. Since we know the PGD of the process we want to manipulate, well, we know what to search for on the higher part of the address. But we also know the virtual address that we want to alter, and therefore we know the first index, and also the others, of course. But we know how to find the first index. What we do is waiting for the PGD PFN in the snoop address, of course. And we double check if the index matches with the index 0 we saw before in a virtual address example. So I will go back to that later if needed. But in any case, the virtual address is composed by index 0, index 1, index 2, and so on, considering how many translation layer we need, and the offset. If the first index matches with this index part of the address, then we are in trigger mode. We need to do something, okay? So what we will do is reply with a cache hit, as we saw before in the diagram. and in parallel request the main memory, the same address from main memory, because we need to obtain the original data to alter, or in this case, to advance the process. Okay, once the data is provided by the main memory, it will look like this. Some attributes, the next PFN, so the base of the next table, and another set of attributes. What we do is we pass back this data to the CCI, and therefore to the main CPU cluster, but we also update the next step PFN. Because if for the first step we have the PGD, we don't know what will be the next step of the translation pointing to. We need therefore to follow the same guidelines, the same addresses that is following the MMU. The MMU will ask for the next address, something that is composed by this PFN plus the index 1 of the virtual address. We update our internal registers. We now search for this PFN for the next step.
And you wait for it.
And we wait
for it to
for this. Next steps, basically the same process, but now we are searching for any PFN that we received before, and a new index. So it will be step 2, step 3, and so on. And we continue the process up to the last level. So we saw the first step. We are seeing the intermediate step, that is basically just iterating and updating the internal state of our machinery. And for the last step, we do basically the same thing, but once we receive the data from main memory, we are not passing it as it is to the CCI, but we will manipulate the content of this cache line in a semantic way. So basically surgically changing either the PFN with the target PA we passed as a attribute at the beginning, or the attributes of access for this entry. What we can do here is absolutely not limited. We have full control basically of the whole virtualization, of the whole translation layer. And of course, we pass this manipulated the data cache line to the main CPU. So basically, in a in a 3-level translation machinery, we wait for the PGD. After that, we use the data to wait for level 1, level 2. We poison and reset. We manipulate and we reset. That's the whole machinery. We're done. Do you think it works? No. Okay. Why? Did I convince you that this thing can work in theory?
No.
In theory.
So what are the hurdles? What are we working against? No, the documentation is fairly clear.
Oh, yeah.
Fairly clear.
Somehow, yes.
You have to read it 10 times, but 10 times.
After 10 times it is clear, yes. Okay, but while you think to why this thing can have problems, I'm gonna go prepare a small demo so I can show you how it actually works. And after that, we discuss why it should not work. Hmm?
But let me give a hint, right?
Yeah.
Here, what really the machine on the last slide is saying is we are really following, you're really shadowing the MMU, right? The MMU does one step, you do one step with it. Once you realize that it's something you care about, right? Because they don't even tell the other things. But once it triggers, you're really following it, right? Following along, like a little buddy, right? As the MMU moves to the next step, you are the one providing, and as you feed off the data, you know what is the next trigger, right? Until the last part where you provide whatever you want. Okay. For this to work, you better be able to look, to be able to see those loops, right? I'll leave it at that. Think about it.
Give me just 1 second so I can prepare the demo. Hmm?
Sorry? If the loop goes out, you will see it. If you are setting the trigger to the right speed, it's just a comparator, you will trigger. If the loop goes out, you will see it. 100%.
If okay, so
The cool thing here, let me add, this doesn't really help you answer this, but once you provide the final data, right? the final manipulated one. Now, the CPU cluster has translated a VA into a PA being the one they manipulated, and that will be cached in the TLB, right? So that association now it's done until it's evicted from the TLB. So your machine will not have to trigger every time this page is accessed. This is why it's powerful, right?
Okay.
Because these translations, once poisoned, are cached and stored in the TLB.
But the TLB flushes usually.
Eventually, yes, in which case the machinery will reactivate.
Very complicated juggling trick if you have a bunch of masters asking for different things and you're.
Of course, if you have multiple masters, you have to be very, very careful.
Mhm.
But you know, you have to just follow the protocol and stay within the what's allowed by the protocol. If necessary, you will have to basically preemptively invalidate from other masters any copy of this feed, right? But
That's a very taxing thing if you have to
it's
preempt every other master to do these things.
doable. I mean,
And then the more you have these masters relying on you, the more you're in the critical path of everything, right?
yeah, I agree that, you know, first of all, we're talking about the interconnected go up to a large number of masters. Snoop-based, pure Snoop-based like this is not always used. You normally use something like called Snoop filter, so you actually, the CCI limits the communication between the parties that actually have that piece of data. And we are talking about page tables here, so it's not, unless you're running a multiple application on, you know, across the cluster.
Yeah.
You typically don't expect that that data is shared between multiple clusters. Here again, remember, we are very surgical about what we're not responding to all groups, only the ones that correspond to the self-translation.
So basically, this is restricted to just one master, the application on the page table that we're trying to manipulate.
Yeah, for now, by master, we mean somebody who participates in the coherence domain. For the one master is the whole CPU cluster, so that has already multiple cores. And then FPGA is another master, but there could be like a DMA, for example. DMA could be cache coherent, but if it doesn't impact with the fact, for example, it doesn't implement a cache internally, they just want to see the latest version of page table, not a problem. We can also respond to that the same way we respond to a CPU cluster. I don't want to distract you from the demo, so.
Okay. So in the screen, we can see the UART0 and the UART1 of our board. Okay. Linux is running using the UART0 as default console. So we can see, yeah, that it works normally. Okay. What I'm going to show you is that if we have a program, in this case, okay, it's just screaming for help on my program, but that's because I was debugging. Still, basically, this program, this user space program, is directly interacting with the UART0, mapping it directly, and is writing this line continuously. That's it. Okay. Neither the process nor Linux is aware of the existence of our machinery in the FPGA side of the board. Now, if we want to change something in our translation, so if we want to virtualize it, for example, we can add a prefix. This prefix is added directly by the FPGA side by two elements. The first one is our Softwareless Nano-Virtualization, and next to it there is a small interface, hardware proxy, that will add a layer of virtualization to the UART machinery itself. What we are doing then is manipulating the translation between the virtual address of the UART to the actual physical page of its registers, and redirect this page to our internal page of the proxy. This thing is done in a seamless way for the process that is continuously thinking that is interacting directly with the UART0. Fine. We can, of course, also use the other UART. I mean, I think it was not a big of a surprise since I'm showing both of them, but yeah, we can start to. Yeah, we can. Just a second. I don't know. Yeah, it's alive. What? Yeah, but it's not. Just a second.
The right to R, 01.
Okay.
Okay, now you deactivated the.
Yes.
So does it make sense what's happening here?
Okay.
Oh, yeah.
So same way, we are passing from UART0 to UART1, also adding a prefix. In this case, we can also add it. I mean, this depends on the proxy or the multiplexer that we are implementing in hardware. But in any case, the idea is the software is still communicating in the exact same way without any change with the UART, and still is not communicating with the same machinery anymore. Does it make sense?
How the server is set up.
What level? Like which?
Yeah, maybe we can on the board, right? We have a pen, like
Yeah.
we can show the different components. So there's the process communicating normally with the directly memory map in the original UART, and there's also the UART1, and then there is your instantiation of the interface in hardware.
I should draw. This will be
That's what you wanted?
okay. Fine. Huh? Yeah. No, I just a very bad drawer. That's my. Yeah. I can try that. Okay. So. Perfect.
Oh, I mean, if you want to
It's
show
a
the
whiteboard.
board, the actual whiteboard.
Oh, that's it. It was for the people online, but yeah, it's fine. It's okay. Yeah. My bad. Okay, so. Okay. This is I will use blocks both for the software side and the hardware side, but I'm gonna explain it. So this is the screamer process. That is just writing on the UART. It is mapped to the UART0 registers. What it does is basically following the normal driver of Linux. It will check if the FIFO for writing is full, or if it is full, yes. If it is not, it's writing the next character. That's it. Fine. Once we activate our FPGA, yeah. Actually, yeah, because we will set, yeah. You're right. Once we activate the SNV, the SNV will interact not directly with the screamer, because he has no, there is not an actual layer in the middle, but with the Softwareless Nano-Virtualization is the machine. It will interact with the MMU of the core, because periodically, of course, there will be a new translation for this address, because it will be evicted by the TLB, because there's been a migration. We don't know. Periodically, not even so. I mean, it's also common and it happens often. So the MMU, once you will try to snoop the address from main memory. Okay. We interact also with the SNV that will follow the steps I showed before in the slides. So from the PGD, following the virtual address that is currently mapped to the UART0 registers, we'll just follow the translation up to the last step. And at the last step, we'll change. Let's assume all the other steps happen normally. The very last step, so there will be a translation, that will be the third, basically. And there will have as PFN the actual UART0 address.
SNV control, right?
Register PFN. Okay? This thing will change inside SNV as something that looks like this. PFN of proxy 0 registers.
The proxy 0 is still memory map, but it's not the UART anymore. It's actually a piece of hardware that we made up, like your Francesco. And basically it looks a lot like a UART, it quacks like a UART, Right? It walks like an UR, but it's not a UR.
It's not a UR. So basically, once this PFN is passed to the mu, the screamer, not knowing, will now redirect to the proxy 0.
And this page table, what's interesting is that these page tables have not been modified. In main memory, they are still the original page tables. The only version of these page tables that are repointed there is only in cache, right? In the TLP. There is no sign that anything has been manipulated. It's only.
Yep.
Why didn't get an attack?
Because maybe the software will check, right, if these are still the correct page tables that they've installed, and everything checks out, right? No problem there.
Yeah.
Yeah. In
Which
fact,
software would have to check it?
The kernel.
may want, or even yourself, you do a translation. Right, do a page table walk.
In any case, exactly as the
But suppose you wanna don't stop doing the virtualization for whatever reason, right? If you lost
Don't
the
stop.
pages.
yeah.
Yeah, you have to be
You
careful when you
cannot do that.
activate and
Yes.
deactivate, of course.
Yes.
yeah.
In
You
this
wanna stop that, you just invalidate what's in cache,
exactly.
and everything is restored exactly as it was.
By the
right?
way, it shows you two use cases. One of them is sent to this proxy, which basically interacts with the UART, adds a prefix to every new line as a state machine that checks for new line, add a prefix, and then actually sends the bytes coming from the screamer to UART 0. That's why you can see the prefix and then help.
Mm-hmm.
In the other case that he showed, it basically not only does that, but then he also redirect to a second UART, which is another device, which is still a real device, which is UART1. So he's doing both, right? You can send to UART1, or you can put a prefix and send to UART0, or put a prefix and send to UART1, which is the second case that he shows on the right.
Yes.
So
So UART 0, what we see here with the prefix is actually not UART, but it's a proxy.
exactly correct. It's something that adds a prefix to the bytes that then go to the UART and then sends the byte to the UART. But every time he sees a new line, it tells to the screamer, hey, UART is busy, you can't send
That's
this
cool.
byte. In the meantime, it's sending its own prefix.
I see.
And then allows the bytes to go through.
And in the other one, it's redirecting it to a different unit.
Correct,
Yes.
entire.
Still
correct.
through another
And
proxy.
add the prefix and add the on
And
top
the
of it.
prefix.
And-
Yes, and doing stuff.
Okay, so now this works, but in the way we presented, it shouldn't.
It shouldn't. Yes. It shouldn't for some reasons. We're going to explore quickly the most important now. We can have multiple series later because there are a lot of, but still,
Good stuff.
thank you. Oh, there will be this forever, no?
You're still in drawing mode? no?
Yep, but I cannot remove it. Oh, it appeared again.
Oh, yeah, there's a little X. so-
No, I need to. Oh, I can see here.
First clear,
Okay. Better. So, I can use this. Perfect. There are some details. We are not actually done. Because the most important element to consider is that since we are talking about cache coherence, cache snoop, and everything is cache space, we are implying that transactions of at least cache line size. And in each cache line fits in our system 8 different entries for the next step. This implies some interesting elements. First one, we cannot now follow the translation just by looking at the snooped address, because the snooped address will give us partial information. Will give us, okay, I'm going to read one of these 8 PTEs, you don't know which one. Perfect. Also, for the next step, not only we don't know which one is the one of interest, but also we don't know the next PFN that will be actually required by the main memory. So we need to consider when we were updating our internal registers, not only one PFN at a time, but 8 of them. In this case, but N is very generic. I mean, we can consider it as much as we want. And even better, since we are talking about cacheability, we are talking about coherent cache, every transaction that happened is being cached. And if during this translation process, we diverge from our target VA, but we are still having a transaction that will end one day after a few steps, there is a chance that when we will actually try to translate the VI of interest, the previous steps can be already main memory. in the cache, sorry, in the main CPU cluster cache. So we cannot follow anymore the transaction as nicely as we saw before.
Right? So the MMU
Yes.
realize that you're shadowing step by step the MMU. But if the MMU, instead of missing in the CPU cache, hits in CPU cache, you don't do this loop to the FPGA and you lost a step. But then you lose all the steps.
All the steps, yeah.
Suppose you start at the caches that are not low, right?
Yes.
Start with the
That's not
translation. You could also offer that, okay, you know what? PGD, great, I got it. Stage level 1, great, I got it. Then you go to the table 2 and you don't eat the table that
Yes,
you expected
absolutely.
because somebody is translating another one.
Yeah.
It was not your cause.
Exactly.
Right?
That's what
So
we
now you won't get any more PGD, table 1 and table 2.
because being cached. That's the point. Yes, exactly.
Why shouldn't work?
So considering just for the so we have solutions since we saw it work. It can work, but it implies some further manipulation. So what I showed today is the vanilla way to do it. So if we have a matching between the size of the translation and the transactions and the size of the PTs, everything will run nice as smoothly as it is now. But since it's not the case, we need to add multiple steps of complexity. And for example, when we are passing the intermediate step back to the CCI, we don't want it to be actually cached anymore. Or better, it can be cached, but we want it to eat for the next time something that will not be in cache, so it will pass again through us. Basically, we need somehow to fix this problem by exploiting still the cache coherence system. There are solutions, they are still work in progress, so we can discuss about it in the future.
There's more elegant, so there's a simple solution. For example, you could just pass and invalidate. Right?
Yes.
I mean, we know that would fix the problem because you pass, you invalidate, the data is used, and by just following correctly coherence protocol, you can actually pass in a way that data is used only once and then invalidate it because you want to use it, right? From the coherence perspective. But it's ugly and we'll have higher overhead.
Exactly. We are very much not going on the minimal overhead here. Exactly.
Make up address.
Yes, we create new addresses that have some kind of additional semantics, and we use these additional semantics to retrieve back what we want from the cache stream. But it needs a whole different discussion because it's messed up.
Yeah, so and right now, right, Francesco showed you a use case that works, which is IO virtualization, so the ability of basically redirecting IO flows. We also have use cases where still a little bit of sort of sizzling work to get basically a transparent page migration for a process, right, that is running, is mapping an area of memory, not IO, and kind of you can move it around dynamically in a way that stays transparent to the software. So you want to move it, for example, from main memory to scratchpad or vice versa. You can do that with this machinery.
Yes.
And then, of course, extension to multi-pages, right? That's awesome.
Yep. So, yep.
Like, what is the resources just for this UART? Like, how much did you use?
For the UART system?
Yeah.
UART plus the SNV machinery, we are talking about the 5% of the FPGA, if not slightly less.
LUTs, VRAM, but like, are you using 5% of all the LUTs?
No. We are using something like 5% of the lookup tables and 1% of the VRAM, roughly speaking. Yes.
Running at max speed or?
We're running at 100 megahertz right now.
Okay.
But we didn't test to synthesize it faster.
Okay.
Yeah. Just because for now it's working, so yeah. It worked. Come on. And also in some very preliminary experiments, where the system is not stressed. Okay, so we have to test that case. We are not having any overhead even staying at 100 megahertz. So yes.
How then you are do a GPU virtualization?
Oh yeah. We can, because right now this will be a problem. So there are some solutions for that. For example, the single root IO virtualization. Sure, there are some solutions, but they also have some kind of drawback. So if you go through a software multiplexing, you are losing because you are going to software. If you go to hardware, you need to instruct your software layer to interact with a new plethora of multiplex I/O. What we can do is being in the middle. So we can do all the multiplexing we want without having any modification to the software. So they will just see a new GPU, and that's it. Thanks. Yeah.
Of course, these techniques, essentially, this is one piece of the puzzle of really a whole set of primitives for full softwareless nano-virtualization.
No, software.
Software.
Software nano-virtualization.
Virtualization, bunch of.
Oh, yeah.
XYZ that need to be supported to actually have proper hypervisor done with this technology.
We are working on that.
Have any measurements on how much overhead, because you say minimal overhead.
Yes, okay. This is more a hope than a actual statement right now. What we saw in the experiments, in the first experiments, is that our overhead is inside the 1% overhead that will be for JLAOs or any other type 1 hypervisors. But I can come back to you once we have better results. Okay.
Alright, so
Thank you for your time.
Yeah. So much debugging.
Oh, yes.
Yes, the chat. You know what? I'm just gonna close my eyes and go to sleep.
This is pretty fun, actually, you were able to the numbers.
What other hardware would you have?
What?
Here, what exactly do you use instead of UR0?
Oh, no, I just wrote a simple proxy in FPGA that will just redirect everything.
Emulating itself as a UR.
Yeah, it
And-
really communicates with this, right? It
Yeah,
still
yeah.
has a connection here,
It
right?
does, okay.
Yeah,
Okay.
because in the end,
I was thinking.
what you output here, this is
Yeah,
the
it's a
actual,
UR
this is
thing.
UR.